Okay, so in this video, we are going to study some examples of applying conservation of energy, and then we are going to briefly talk about power, and that will conclude our discussion of chapters 6 and 7. So, what we had learned so far in the previous videos was the work kinetic energy theorem, which just says that net work equals the change of kinetic energy. We also learned the definition of potential energy, which says that the work done by a conservative force is equal to the negative of the change of potential energy. And at the end of the last video, I showed you that if you put these two together, then you get this very useful equation, which can be written as, after a few lines of algebra, it can be written as initial kinetic energy plus initial potential energy plus W other equals final kinetic energy plus final potential energy. This equation is called the equation of conservation of energy, and in physical content it's identical to the work kinetic energy theorem. So there's really no difference between the work kinetic energy theorem and this equation over here, except that the conservation of energy equation is a lot easier to use than the work kinetic energy theorem. So you can do every problem in chapters 6 and 7, both chapters 6 and 7, just using the conservation of energy equation. So we will just be using this equation for doing all of our problems. So we're going to first start with some examples of applying this equation. After looking at some easy examples, I'll show you a few examples where you have to apply this equation in conjunction with Newton's second law. So we'll look at some of those examples as well. All right, so let's start with the example on slide 36. I'll let you read this for a moment, and once you've read the problem, then come back, resume the video, and see how I approach it. Okay. So the problem is saying that you have a ball of mass 2 kgs, which is thrown vertically with a velocity of 10 meters per second. And for the first part, we are ignoring air resistance. And the question is asking, what is the maximum height the ball is going to reach? So the ball is launched from the ground, and you know what velocity it's launched with. V initial is 10 meters per second. So the question is, what is the maximum height it's going to rise to? Now, your first instinct when seeing a problem like this might be to just use kinematics. And that's absolutely fine. In fact, when I teach kinematics, this is one of the first examples that we do in class, calculating the maximum height an object is going to reach. However, kinematics is not necessarily the easiest way of doing problems. Conservation of energy techniques, particularly this equation in the red box over here, is often far more easier to use than kinematics and Newton's second law, right? So in general, you should always see if you can solve a problem using energy techniques before trying anything else. So let's try applying this equation. Let's try applying our conservation of energy equation here. So let me just write it down again. It's already written down, but I might as well just write it again. Equals k plus u. What is the initial kinetic energy? Remember, the formula for kinetic energy is 1/2 mv square. So what is the initial kinetic energy? It's just going to be 1/2 mv0 square. What is the initial potential energy of the ball? The formula for gravitational potential energy is mgh, as we saw in the last video, right? And remember, for gravitational potential energy, you can choose h equals 0 wherever you like. Typically, it's easiest to choose h equals 0 at whatever is the lowest height in the problem. So the gravitational potential energy since is mgh, and so h is equal to 0 on the ground, so it's just going to be 0. Now what was W other? Remember that W other, as explained in a lot of detail in the last video, W other was the work done by two types of forces: external forces and non-conservative forces. Non-conservative forces means friction, air resistance, and all that stuff. So we're being asked to ignore air resistance. There is no external force on the system. The only force acting is gravity, which is a conservative force. So W other is 0 as well. Okay. Now let's consider the top position. So the final position is the top position. At the top position, what is the final kinetic energy of the object? So since it's at the top, it comes to a rest, its kinetic energy is going to be 0. What is its potential energy? Its potential energy would be mgh. So let's put that down. And h obviously is the height that it rises up to. And we have this nifty equation, 1/2 mv0 square is equal to mgh. The m cancels out and you can solve for h. H is just going to be v0 square divided by 2g. And this is exactly the same answer that you would have obtained if you used kinematics. But you can see that it's so much easier to use the energy conservation equation. Okay, now let's try the second part. What maximum height would the object reach if the average force of air resistance was 5 newtons? So when it says average force of air resistance, it's asking us to just pretend that the air resistance force is constant, which it really isn't. So air resistance force is not constant at all, but for the purpose of this problem, we'll just assume that the air resistance force is constant and it's 5 newtons. So what maximum height would the ball reach if there was an air resistance force acting on the ball? Okay, so this is the second part. Right, so once again, you can do this problem using Newton's second law. You could consider all the forces acting on the ball. Then you could calculate, you can do force equals mass times acceleration. At force equals mass times acceleration, solve for the acceleration, and then use the kinematic equations to find out how high the ball is going to rise. That is absolutely fine. You can do it if you want. But we want to use our new friend, the conservation of energy equation, to solve these problems. So we are not going to adopt that approach at all. We are going to try to use our conservation of energy equation. So let's start with our equation again. K initial plus U initial plus W other equals K final plus U final, right? The initial kinetic energy is 1/2 m v0 square. The initial potential energy, as we just discussed, is 0. This time we do have something to put under W other, because W other is the work done by external forces and non-conservative forces. There's no external forces, but we do have a non-conservative force, which is the force of air resistance, right? We need to figure out the work done by the force of air resistance. Now, recall from our earlier lecture the definition of work. So the work done by a constant force, and I'll just write, the work done by a constant force is equal to the force multiplied by the distance multiplied by cosine of the angle between the force and the displacement. And remember that this formula applies when the force is constant and the object is moving in a straight line. So both those conditions are true here, so we can apply this formula. So while the object is rising up, the air resistance force, which way would the air resistance force be acting? It would be acting downwards, because it always opposes the motion. So Fd is acting downwards while the object is rising up. And so what is the work done by Fd? So you would do magnitude of the force. So that would be, I'll just calculate it over here. Magnitude of the force, the distance that it rises up, which is h in this case, times cosine of the angle between the force and the displacement. The displacement is upwards because the object goes from the bottom to the top. The air resistance force points downwards, and so the angle between them is 180 degrees. And I'll just write pi because I don't have room to write 180. Okay, and what is cosine of pi? It's -1. So the work done by the air resistance force is minus Fd multiplied by h. Fd multiplied by h. Okay. Notice that this work is going to be negative. As we saw, we got this minus sign, and that makes perfect sense because the air resistance force is not getting its way. So it's doing negative work. So Fd times h. All right, so now we can go back to the right-hand side, finishing this equation. So let's do the right-hand side. The kinetic energy in the end is 0 because it comes to a stop, and the potential energy is mgh. And now we have to solve the simple algebraic equation, rearrange it and solve for h. So h would just be half mv0 square divided by, so you would move the fdh to the right side and then divide both sides by mg plus fd, and that's the answer. All right. Okay, let's do the third part of this problem. So the third part of the problem, you are taking air resistance into account, right? And the ball starts from the highest point that it got to. The answer was, I think the answer over here, if you plug in all the numbers, the answer is going to be 4.06 meters. Okay, so in the third part of the problem, the ball is starting from that height, that maximum height that we just calculated. But before it hits the ground, you've moved the spring underneath the ball. So the ball sort of lands on the spring. So it's starting from the top, but now you've placed the spring underneath, right? Let's just imagine the ball is made of metal and the spring is magnetized or something like that. And so the ball sticks to the top of the spring, right? So the question is, how much is, okay, so the spring brings the ball to a stop at a height 1 meter above the launch point. So this distance is 1 meter. And this distance, we already know the point from which the ball starts dropping. We calculated that in the previous part. That's 4.06 meters. Okay, so the question is, how much does the spring compress? How much does the spring compress before the ball stops? So we have to calculate this compression of the spring. That's what we are trying to find, right? Okay, this is the initial and this is the final state. All right, so how do we find that? Let's just apply our equation. K initial plus U initial plus W other equals K final plus U final, right? Initial kinetic energy, now the initial point is at the top, right? The initial point is at the top. The final point is when it's landed on the spring and come to rest. So at the top, the initial kinetic energy is going to be 0. The initial potential energy is going to be mg. Mg, okay, I like to work in letters usually, but this time I'll just work in numbers because it's a little bit easier to see. mgh. All right, there is work done by the air resistance. The problem says that the air resistance acts the entire time the object is moving. So what is the work done by air resistance? We can calculate it in exactly the same way that we calculated it before. It's going to be the air resistance force multiplied by the distance that the object moves, right? And remember that while the object is descending, while the ball is descending, air resistance, which way will it act? Remember that air resistance always always opposes the motion. So the air resistance force will be acting in the upward direction while the ball is descending. So once again, air resistance will do negative work, right? Friction, air resistance, these forces always, like kinetic friction, air resistance, these forces always do negative work. So this is going to be minus Fd times what distance does the object descend? It started from 4.06 meters and stops 1 meter above the ground. So that's going to be 3.06 meters. So I'm using variables for everything else except for the distances, just so it's easier to see. All right, that is the work done by air resistance, and that's all that goes in for W other. Now we do the final configuration. So the kinetic energy after it comes to rest is obviously 0. What about potential energy? Notice that there are two types of potential energy involved here. So there is gravitational potential energy because the object is at a certain height, and there is also spring potential energy because you've got a compressed or an expanded spring, right? A compressed spring in this example. So you have to take both of them into account. So the gravitational potential energy is going to be mgh. So it's going to be mg times 1. And what about the spring potential energy? Spring potential energy is just, formula for that is just half kx squared. K is given and x is what we are looking for. And we are done. So this is our equation. All you have to do now is just plug in all the numbers. We have numerical values for everything. And you just have to solve for x. And I'm sure you can finish that on your own. So this is an example of applying the conservation of energy equation to solve a problem. So there are many other examples on the PowerPoint. Okay, so I think it's probably a good idea to work through this problem. This problem involves a little bit of ideas from chapters 4 and 5, Newton's second law. So I think for that reason, I'll just go over this problem. Okay, so let's work through this one. So once again, please read the problem first and make sure that give it a try yourself, and only then look at how I work it out. Okay. So what's this problem saying? It says that there is a truck which starts at the bottom of this incline. The incline angle is given. Let's just call it theta. And the moment it's at the bottom of the incline, the driver locks the brakes. And so the truck skids all the way up. Right? So you only need to take kinetic friction into account. The wheels of the truck are not turning. It's only friction. The kinetic friction is the only type of friction that's applicable, right? Okay, so the truck skids all the way up to a certain height. So let's say that this is the height that the truck gets to. We'll just treat the truck as a point mass. So the truck is starting at the bottom, and then it gets to this height over here. And that's where it stops. And the question is asking, we're only going to do the first part, and I'll let you try the second part yourself. How far will the truck skid before it comes to a rest? So you have to find this distance. You have to find this distance. Let's just call this distance d. So how far does the truck skid before it comes to a stop? All right. Okay. Now, this problem is entirely doable using the techniques of chapters 4 and 5. So you can set up Newton's second law on this truck. You can do net force equals mass times acceleration, solve for the acceleration of the truck, and then apply the kinematic equations to find out how much distance it's going to cover with that acceleration until it comes to a stop. So that's totally doable. However, we're going to use a different approach, right? Okay, there is one thing that we need to do. We do need to set up the forces because we'll need to calculate work. So we do need to set up the forces while the truck is going up the incline. So while the truck is on its way up the incline, let us consider all the forces acting on the truck. And to make the diagram a little less cluttered, I'll get rid of this. So what are all the forces acting on the truck? So please see if you can identify the forces yourself. The forces would be the force of gravity acting down. There would be a normal force which is perpendicular to the surface like this. Then there would be, since the truck is on its way up, there would be a friction force which is acting in this direction. And that would be kinetic friction. Remember, there are two types of friction, but the one that applies here is kinetic friction. And that's all. That's all the forces that are acting on the truck, right? Okay. Now, okay. So we can do one more thing here. We can figure out what the friction, what this Fk is. So what is the formula for kinetic friction? So the formula for kinetic friction is mu k multiplied by the normal force, right? Let's see if we can make a little more progress here and get rid of the normal force. So to do that, we can resolve the forces into components just as you would do in chapters 4 and 5. So let's break up the, you know that on an inclined plane, you choose one axis along the incline and another axis perpendicular to the incline. So, and you break up all the forces into components, the ones that don't lie along these axes. So Fn is already along our perpendicular axis. Fk is along our parallel axis. So we just need to break up the mg. So let's break up mg into two components. We'll make one component like this. And another component like that. So these are the two components that we are breaking up the mg into. And you know from geometry that if this angle, if the incline angle is theta, then this angle will also be theta, which means that the component that's perpendicular to the incline would be from SOHCAHTOA, it would be mg cosine theta. And the other component over here is going to be mg sine theta. This is all stuff from vectors and earlier chapters, right? Okay, so now we can apply Newton's second law in the perpendicular direction. So Newton's second law is F net equals mass times acceleration. We're going to apply that in the perpendicular direction. Perpendicular to the incline is what I mean. So we will just choose the upward direction to be positive. So in that case, Fn minus mg cosine theta would be equal to mass times acceleration in the perpendicular direction. Clearly, there is no acceleration in the perpendicular direction. So we get 0, mass times 0, which is equal to 0. And so from here, we can just solve for Fn. And Fn is equal to mg cosine theta, right? Once again, this is all stuff that you've seen in chapters 4 and 5. So there's absolutely nothing new here at all. This is all old hat. Okay, now let's plug this Fn into the formula for Fk and get the force of kinetic friction. So Fk is equal to mu k times Fn, as we had written earlier. So that's going to be mu k times mg cosine theta. All right, so that is the friction force. And we've just used Newton's second law a little bit to express it in terms of mg and theta. All right, and get rid of Fn. Okay, now we are going to now apply k0 plus u0 plus w other equals k plus u to this problem, right? Our initial state would be when the truck was at the bottom, and our final state will be when the truck is all the way at the top where it stopped, right? What is the initial kinetic energy of the truck? The initial kinetic energy of the truck is half m v initial square. The v initial is given is 35 meters per second. What is the initial potential energy of the truck? Again, we'll just choose h equals 0 to be our at the ground. So that means the initial potential energy would simply be mg times 0, which is just 0. What is is there a W other in this problem? Yes, there is friction, and so we need to calculate the work done by friction, right? So the work done by friction would be the magnitude of the friction force times the distance that the object moves, and that distance is the unknown quantity that we're looking for. I might as well draw it in again. The distance is this d. So the work done by friction would be Fk multiplied by d times cosine, times cosine of the angle between the friction force and the displacement. The displacement is up the incline, the friction force is down the incline. So it's just going to be cosine of, I might as well just write that, cosine of pi again, which is -1. And so we are done with the left side of this equation. The right side of this equation, what is the kinetic energy when it gets to the top? The answer is 0 because it stopped over there. And what is the potential energy when it gets to the top? So that would be mg times this height h. Okay, so mg times h. Our goal is to solve for d. So we already have a nice equation from which we could solve for d. There is one thing, we just want to get rid of quantities that we don't know. We can get rid of the Fk by plugging in mu k mg cosine theta. That's why we did all those things in the beginning. What about this h? Now let's go back to our diagram. I'll just draw it here again. It's just a pain to go back and forth. So let's say that the truck starts over here, stops over here. This distance is d. This angle is theta. This h is what we are interested in. That's the h that goes in our equation. What is the connection between d and h? Clearly, using SOHCAHTOA, h is equal to d sine theta. Yeah, h is equal to d sine theta. So we can just get rid of h that way. So now all we have to do is just plug in the quantities that we know and just solve for d. So 1/2 m v0 square plus, instead of Fk, we're going to write mu k mg cosine theta. Actually, the cosine pi will be a -1, so you'll have a negative sign. Minus mu k mg cosine theta multiplied by d is equal to mg times d sine theta. So now you have this simple equation from which you can just solve for d, and you just rearrange this equation and solve for d, and the answer would be 1/2 m v0 square divided by mu k mg cosine theta plus mg sine theta. If I did that correctly, factor out the d. Yeah, mu k mg cosine theta plus mg sine theta, and that's the answer. And this method, if you do this problem using Newton's second law and kinematics and all, that's quite tedious. But this method, as you can see, is very, very brief, and you get the answer instantly. Okay. All right. So if you've thought that this problem or any problem that I do in the lectures, this is also what I tell students in class, that if you at first have a feeling that, oh, I would have never been able to figure this out myself, that's completely normal. So don't let that discourage you. What you really should do is make sure that you understand how I did it, and then put away your notes and try to solve the problem yourself. If you can solve it yourself, that means you've fully understood it. If you get stuck somewhere, still don't look at your notes. See if you can figure out why you're getting stuck and get to the answer yourself. If that doesn't work, then maybe take a peek at your notes and still try to do the problem yourself. But keep doing the problem over and over again until you can just completely work it out yourself without looking at the notes. That's the best way to learn physics. Okay. All right, so let's look at some more examples. So all of these are good examples that I've handpicked to help you understand the material nicely. So these two are worked out on the slide. This is another very good example. I think you should be able to do this on your own. So please give this one a try. Okay, so what we're going to do next is we will look at a few examples of problems in which you have to apply both Newton's second law and conservation of energy. Okay, one example of that is the problem on slide 41. I'll let you read this problem and see if you can work it out yourself. When I teach this in class, I usually have the students, I assign this as a top hat question, and I give the students a few minutes to see if they can get to an answer. And only then, after all of them have put in an answer, only then I start working it out. So I would highly recommend trying this, giving this problem a try yourself and see if you can figure it out. And only then, after you've really given it a try, then look at how I work it out. All right, so what we have in this problem is this snowball, this hemispherical snowball, and a skier who starts at the top. We'll just treat the skier as a point mass. And then somewhere over here, so she starts skiing down this huge mound of snow. Somewhere over here, she loses contact and flies off. Right? Okay, so the question is, at what angle alpha does she lose contact? What is the angle at which she loses contact? So if we draw this vertical line, and if we draw this line over here, the question is asking, what is the angle at which she loses contact? Oh, it's alpha in the diagram. I'll just use theta. So what's this angle theta at which she's losing contact? So how do we do this problem? Well, let's consider all the forces on her. Let's start applying Newton's second law and consider all the forces that are acting on her when she's over here. So this is the point at which she loses contact. The point in the middle, she hasn't lost contact yet, right? So let's analyze all the forces that are acting on her when she is at that point. What are the forces acting on her? So there is the force of gravity, which is acting straight down. There is a normal force, which is acting in the radially outward direction like this. So there's this normal force, right? These are the only two forces that are acting on her. Okay, now when you do Newton's second law analysis, what you do is you break up the forces into, you choose a convenient x-axis and a y-axis, and you break up the forces into components along those axes. That's what we did in the last problem. So when an object is moving along a circular path, if an object is moving in a circular path, then a very good choice of axis is the radial direction and the tangential direction. This should have been clarified in chapter 5. So you might have heard about this in chapter 5. So that's what we're going to do here. We are going to break up the forces. We are going to choose an axis in the radial direction and an axis in the tangential direction. And we're going to break up the forces along those axes. The radial direction is obvious. It's this red line, right? The dashed red line is our radial direction. The tangential direction would be tangent to the circle. I'm not going to draw it just because it'll make the diagram messy, but I'll try anyway. That's our tangential direction. Okay, so we're going to break up the forces into components along these two directions, right? Fn is already in the radial direction, so there is no need to break that one up. Mg could be broken into two components, and I'm going to call the angle, this angle, as theta. So I'll get rid of this theta here. I'm going to call this angle as theta. Okay, so theta kind of tells us where the person is, right? So let's go ahead and break up mg into two components. So the two components would look like this. One of them would go in the radial direction, and the other one would go in the tangential direction. All right. The angle, we have the angle theta. I might as well just get rid of this as well, just to make the diagram less cluttered. Okay. So if theta is this angle, then this angle is also theta, right? And so from SOHCAHTOA, the radial component of mg would just be mg cosine theta, and the other component would be mg sine theta, which I'm not writing because just to reduce clutter. Okay. All right. So now we have resolved the forces into components. I might as well just write it, mg sine theta there. Now let's apply Newton's second law in the radial direction. All right. So how do we do that? So what we do is we Newton's second law is F net equals mass times acceleration. Now, in order to calculate F net, we need a sign convention. We need to decide which direction is positive and which direction is negative in the radial direction. There's a very good sign convention that you can use here, which is that radially inwards is positive. So that's a great sign convention that goes with our choice of axis here. The sign convention is radially inwards is positive. I'm just writing as radially in as positive. Radially inwards is positive. So with that sign convention, mg cosine theta should be given a positive sign. So mg cosine theta minus fn is radially outward, so it's negative, is equal to mass times acceleration. Now, what is the acceleration of an object that's moving in a circle? If you think back to chapter 5, where you studied centripetal force, or centripetal acceleration, that is the acceleration of an object moving in a circle. It's a centripetal acceleration which points towards the center of a circle. Whenever an object moves along some curve or along a circle, it has to have an acceleration which is pointed towards the center of the circle, which is called the centripetal acceleration. And the centripetal, the word centripetal literally means center seeking in Latin. So the centripetal acceleration always points towards the center of the circle, and the formula for that is v squared over r. So this is from chapter 5. The radius of the circle is r in this case. So it's mv squared divided by r. So from here we can solve for the normal force. So the normal force is going to be mg cosine theta minus mv squared over r. Okay, now why did we solve for the normal force? The reason is the following. We know something about the normal force when the person is going to lose contact. Can you tell me what happens to the normal force when the person loses contact with the ground? I mean with the ice mound? The answer is the normal force will vanish. The normal force will become zero, because the normal force only arises because an object is in contact with the surface. if the object loses contact with the surface, there is no more normal force, right? So when the person loses contact, then Fn, when the person loses contact, Fn is practically equal to 0, right? So we could set Fn equals 0, and we could solve for this angle theta at which they lose contact. There's some hope there. The problem is we don't know what the velocity is going to be when they lose contact. So let's redraw this diagram here again. Let's say that they lose contact at this particular angle, at this theta. This is the angle at which they lose contact. So Fn becomes equal to 0 at that point, right? I need to know what is the velocity of the person at that point. That is where conservation of energy comes in. Right? So let's calculate what velocity will the person would have at this point, assuming they start with 0 velocity at the top of the ice mound. Okay, so this radius is r, this radius is also r, and let's draw this height. What will the height of the person be when they lose contact? By geometry, since this angle is theta, this will be r cosine theta. So the height would be r cosine theta, right? So we want to know what is, so velocity is 0 over here. We want to know what is the velocity over here, right? We are ignoring friction. So can you see how you can set up conservation of energy to find the velocity at this point? So you would do k initial plus u initial plus w other equals k final plus u final. The initial kinetic energy at the top of the mound is 0. The initial potential energy would be mgr. There is no external force or non-conservative friction force, so there is no w other we need to worry about. The kinetic energy at the point where they lose contact is going to be half mv square, where v is the unknown velocity. And potential energy would be mg times the height, and the height, as we can see from geometry, is just r cosine theta. So this equation allows us to solve for the velocity at the point at which they lose contact, right? So let's go ahead and solve it. So it looks like this equation will simplify. The m's cancel out. If you multiply the whole equation by 2, then you can just rearrange this and get v square is equal to 2gr 1 minus cosine theta. Great. So we have found the velocity of the person at any angle, and in particular, if theta is the angle at which they lose contact, then that's the velocity at that particular angle. So now we can put this missing piece into the equation that we derived earlier. So we had seen that Fn is equal to mg cosine theta minus mv square divided by r. We can plug this v square in and just get rid of it. So Fn would be equal to mg cosine theta minus m over r, and then plug in what we got for v square, which is 2gr 1 minus cosine theta. The r cancels. So it's mg cosine theta minus 2mg 1 minus cosine theta. And we could probably simplify this a little bit. So this is mg cosine theta plus 2mg minus 2mg, sorry. I'm just doing algebra here. I'm not doing anything fancy. Minus 2mg plus 2mg cosine theta. So this is 3mg cosine theta minus 2mg. That is what Fn simplifies to. So all this was just algebra. I need not have even done that. So now we can finally find the theta at which the person loses contact, using the fact that when they lose contact, and I'd written this earlier too, when they lose contact, Fn is equal to 0. So let's set Fn equals 0. Now we can, so let's just go ahead and set Fn equals 0. And then, so you get 0 is equal to 3 mg cosine theta minus 2 mg. You can divide both sides by mg, and so you get 0 is equal to 3 cosine theta minus 2. So cosine theta is equal to 2/3, which means theta is equal to a cosine inverse of 2/3, which is approximately 48 degrees if you plug that into a calculator. And so 48 degrees is the angle at which the person loses contact. All right, so just to summarize what we did here, we knew that the Fn will be 0 at the point when the person loses contact, right? So what we did was we first used Newton's second law to derive an expression for Fn, and that's what we did over here. We derived an expression for Fn, right? We could not set Fn equals 0 in that expression. I mean, we could have if we wanted, but the problem is we didn't know what the velocity would be at the point where she lost contact. So to find the velocity at any given angle, we used the conservation of energy, and we derived the velocity as a function of the angle. So we could, this expression tells us what is the velocity for any angle theta. So we plug this into our expression for Fn over here and simplified. And now we got Fn in terms of theta. And then we set Fn equals 0 and just solve for theta. So we had to use both conservation of energy and Newton's second law to do this problem. So this problem is a bit hard. And so again, you might have that feeling that I wouldn't have been able to figure this out myself. But please go over this problem a few times, see if you can work it out yourself. Explain it to yourself. That's the best way to learn. And once you can explain this problem to yourself, you will have made quite a lot of progress in understanding all of these concepts. So the next slide has a very similar problem. So we did this one. This one is very, very similar. So I would recommend trying this on your own. And okay, so that concludes all the examples that I had on the PowerPoint concerning energy conservation. We just have one very brief little concept left in this chapter, and I'll just quickly go over it. And that is the concept of power. So we've talked about work. So you know what work is now. We've not talked about how quickly that work is done, right? So power is a concept that tells you, that quantifies how fast work is done. So if an amount of work delta W is done in time delta T, then the average power is delta W divided by delta T, right? That's called the average power. It's just joules over seconds. So if 10 joules of work are done in, say, 5 seconds, then the average power is 10 divided by 5, or 2 joules per second, right? The unit of power is watt. Joule over seconds is defined as watt. So the unit of power is just watts. So a watt is defined as a joule per second. Sometimes we are more interested in the instantaneous power rather than the average power. So instantaneous quantity just means that you want to know what is the power not over a large interval of, say, 2 seconds or 10 seconds, but what is the power at a particular moment in time. So that just means the limit of this quantity, delta W divided by delta T, where the delta T is a vanishingly small interval, right? So this quantity is called, is nothing, from calculus you know that this is just the definition of the derivative. So this is just dW dt, and that is the definition of the instantaneous power. So instantaneous power is just dW dt, the derivative of the work done. Right? There is one other thing that you can do here. Suppose there's a force F acting, and that acts on an object and makes it move through a distance dx. So the work done is F times F dx, right, over that tiny interval. So let's call that dW. dW is the tiny amount of work done as the force pushes an object through a distance dx. Suppose this happens over a time interval dt. So in that case, the power would be dW divided by dt. So that's F dx divided by dt. What is dx over dt? It's just velocity, right? So that's just F multiplied by velocity. In 3 dimensions, this formula just simplifies. This formula just becomes F dot v. So I'm not showing you the proof for all 3 dimensions, but I'm just stating the formula here. So power is the dot product of the force and the velocity. If the force and the velocity both point in the same direction, then the dot product just becomes ordinary multiplication, because it's F multiplied by V multiplied by cosine of the angle between them, which is 0. So it becomes F times V, as I just showed here. So that this formula is also useful. Power is equal to F dot V. In the PowerPoint, I have a couple of worked examples. So this example is worked out. This one you should be able to do yourself, the one on slide 45. I've also given you a hint. So see if you can do this one yourself, and if not, you can just ask me or Justin during office hours. And that concludes our discussion of chapters 6 and 7. So I'm just going to end the video here.